students are in a separate Zoom. Oh, yes, there is a YouTube live link and they can see us in YouTube live.
Yeah. It.
God.
That's why I don't understand machine.
Okay, hello and welcome everyone to the live session for week 2 of our course, Introduction to Quantum Computing, Quantum Algorithms and Qiskit. So in week 2, we observed there are a couple of questions around course logistics and also around assignments. So one of the requests that we have been receiving is around extending the deadline for week 2 assignment. So week 1 assignment deadline was extended because the course registration date was extended. Week 2 assignment, while we are trying to extend the week 2 assignment date, I don't know if that would be a possibility or even if a day or two extension would help. So today our primary focus would be around helping you all do both the assignments. So we'll be discussing about the concepts that we are trying to percolate into your minds around in week 1 assignment as well as in week 2 assignment and how to do that. So we'll discuss the assignments in detail today. And then we're also trying to clarify a couple of conceptual questions that have been coming from both week 1 and week 2. Okay, and before I go ahead with the questions, so there's a post that I have put up in the FAQ channel of Discord. So if you guys are on Discord, then you'll be able to see under information there's a channel called FAQ. And in that, I've put up a link or to a document file. So you can just download that. There were a couple of requests on what are the different links that have been shared in week 2, and some of them are not very visible, or you're not being able to copy the video. So please feel free to use that link. And maybe, yeah, I see Prabha joining. Okay, so I'll quickly go over that link till that time and show you guys what are the different links. So the different links that we covered in week 2 content, be it where you can see all details about hardware, simulator services, the different documentation and your jobs and all details. So you can go to catalog, quantum-computing at IBM.com, where you can see both Quantum Composer and Quantum Lab. And if you just type in /catalog, you can see your simulator and services and hardwares that are available. Also on the quantum volume, I've put in the Jupyter Notebook. This is the link to the Qiskit textbook. So as we have been saying, Qiskit textbook is a fantastic resource for self-learning. So this is again from Qiskit textbook, where you can see how to measure quantum volume. And I've also given the link to the actual paper. There were a couple of questions around in here around what is gate fidelity and several other things. So I'll just try to mention in very brief that what are each of these parameters. So there are several parameters that quantum volume takes into consideration. As pointed out, for gate fidelity is at what error rates do gate operations move bits from one state to other state. So that's kind of basic way you can understand gate fidelity. And there are several others like calibration errors and circuit optimization coherence and all the other details that are present in the video lecture, and I've explained each of them. And I can put in more details of what each parameter means and how it contributes, and you can also check in this particular link for details about each of them. Then there are some queries around the concepts which we are going to discuss in detail, and there are other learning resources and education and research resources that I've put in this particular link. So now let's move to the week 1 assignment. So in week 1, there were a couple of questions around the assignments, and the first question that probably Prabha, I'll ask you to clarify. It is around the vector representations of the qubits. So would you want to explain how to do a vector representation of a 2-qubit or a 3-qubit?
Yeah, sure. Thanks, Anu, and welcome everyone to the second live session. It's good to see a lot of enthusiastic participation both in the Google forum as well as on Discord, and also special thanks to all our TAs and mentors who are answering all the questions. Okay, so let me share screen, I guess. Okay, so the question was about how do we visualize these multi-qubit states, right, as matrices or column vectors, which is what we typically do, right? So like last time, I'm going to just number the questions or concepts that we cover. So the question is about multi-qubit states, right? Starting with 2-qubit, 3-qubit, etc. And how do we visualize them, right? So right? So the canonical association always is that we identify ket 0 with a column vector which is 2 entries 1 and 0, and we identify ket 1 with the column vector 0, 1, right? So let's do now the simplest example of a 2-qubit space, right? So the 2-qubit space now has, if you think of this as just 2 registers, right? And these are 2-qubit registers which can exist starting with just this basis. By the way, this is what we call the computational basis, just to remind everyone, right? So can one first identify a computational basis for the 2-qubit space, right? What is the equivalence? What is the equivalent of a computational basis for the 2-qubit space? So what we need to do is to take tensor products of this pair of states, right? So think of this as essentially a 2-bit binary string to begin with, right? See, that's how we made the bit to qubit association. We took a single bit X, right? And then we associated a pair of orthogonal states to that. Similarly, take a 2-bit string now, right? So if you want to call this XY, then you know that this can take one of 4 possible values, right? 0, 0, 0, 1, 1, 0, 1, 1. So correspondingly, you can write down 4 states here, right, of this form. And I will just explain what this symbol is. So what do I mean by this symbol, right? This is what is called a tensor product, okay? And I should mention that there are multiple ways of representing this. So often I think in my lectures, I omit the tensor product sometimes and I write it like this in a subsequent lecture. In my early lectures, I did not discuss multi-qubit systems. These can also be simply represented like this, okay? So the idea is that this represents the first register and this represents the second register. In a circuit picture, this is the notation that we follow, that this will be the ket 0 and this will be the, so maybe I should put a different ket here. So the first register is sitting here and the second register is sitting here, okay? And how do I now represent this as matrices? So what does this tensor product actually do? So let me show you with just this example itself. So I want to take the tensor product of 1, 0, tensor 1, 0, right? So the way this works is that you take this. So first of all, you understand that now we have gone from what is a two-dimensional linear vector space to now a four-dimensional linear vector space, because there are four possible bit strings in the classical case. That translates to four possible orthogonal states in the quantum case, and that then implies a four-dimensional complex linear vector space. So what we expect to see are column vectors of length 4, right? And the way this works is you take the first entry here, which is 1, okay, and multiply every entry of the second vector with this first entry. So this is 1 times 1 0 and 0 times 1 0. So I'm writing a kind of block form for this. Okay, so this is how I get my length 4 vector. And so what is 1 times 1 0? That is just 1 0, right? And 0 times 1 0, so that becomes 0 0. So this is the 4 cross 1 matrix, or the 4 column vector, length 4 column vector, that I will associate with 1 0 tensor 1 0. More generally, right, if I want to represent this, so I have AB tensor CD, okay? So that becomes, now you can work this out with me, A times CD and B times CD, okay? So note that there's a certain ordering to this tensor product as well. This is, I'm just simply giving you the definition, right? This is simply the definition of this tensor product. So this gives me now again a 4 column vector, which is AC, AD, BC, BD, okay? So this is the general rule or formula for how you would do this tensor product, okay? And so we can do a few more examples. We can actually do 0, 1, okay? What that means in a circuit picture is I have the first wire set to 0 and the second. So to me, always when I go between this kind of a notation to the circuit, it's the first register or the first wire which is in ket 0, the second register is in ket 1. Okay, this 0 1 state is nothing but 1 0 tensor 0 1, and I hope you can now read off with me that this becomes 0 1 0 0, right? Okay, finally we can do another example here, which is 0 0 0, right? So let me now take this to a 3 qubit state, okay? And the same rule holds, right? You just have to keep doing this sequentially, okay? So now let's do this example. So you can do it any which order, but let's do these two first, right? Because we've done this already. So this is 1 0 tensor. Now there's a 4 column vector here with entries 1 0 0 0, right? And now what do I get? Remember, this is a 2 column object tensoring a 4 column. I mean, a length 2 tensor a length 4, or a 2 cross 1 tensor a 4 cross 1. This gives me an 8 cross 1, right? This gives me a column vector of length 8, right? Because the first entry has to multiply. This is multiplying this entire column vector as a scalar. This entry is multiplying this entire vector again. So this basically is 1 times 1 0 0 0, 0 times 1 0 0 0. I apologize for the space thing, but I can write this out very clearly here. So you see now this is 1 0 0 0 0 0 0 0. Okay, so that's my 8 column vector of length 8, right? So this is now sitting in a, this belongs to an 8 dimensional space. Okay, so you can work out similar products like, 0 plus, for example. So Anu, I think this is the last example I will do. We're back to the 2 qubit scenario. Okay, so recall that 0 is just 1 0 now. Tensor plus is what? 1 over root 2, 0 plus 1. So it becomes 1 by root 2, 1 by root 2, right? So then this becomes, you again have to multiply 1 with this entire column vector, 0 with the entire column vector. So this becomes 1 by root 2, 1 by root 2, 0, 0. Okay, so I hope this clarifies the idea of the tensor product and how to represent multi-qubit systems, states of multi-qubit systems as column vectors. Right. Back to you, Anu.
Yeah, thanks, Prabha. Thanks, Prabha. So you actually covered two questions. So there was a question around week 2 assignment.
Okay.
So in week 2 assignment, there's a question on what is the tensor product expansion of a 3-qubit state. And people have been confused in for both question number 8 and question number 10, wherein we are saying that, okay, there's a Bell state which is to be measured in a plus minus basis, and what would be the measurement outputs. So people have been asking whether the notation is what is the typical notation? Are we considering least significant bit to left to right or right to left? Because Qiskit has a different notation and some physics textbooks have a different notation.
Right. So as I mentioned here, this is the sort of convention that I have. So maybe let me just explain this with the Bell state circuit, right? Let me call it the Bell state preparation circuit. Okay. The way I would explain this, so let me draw the circuit first. So by now everyone should be familiar with this. This is a 2-qubit circuit, right? Which has, you start off with a Hadamard, right? And then you apply a C0, right, on between the first and the second registers. Now, my input state is 0, 0, right? Then what is the output state? I guess this was probably an example that was worked out in the lectures. Let me work out a slightly different example. So let me work out the example of the 0, 1, okay? So what is the output state now? That's the question. So the way I would analyze the circuit is as follows, right? So I start with 0, 1 like this. So this is the sequence. So when I write 0, 1, like I emphasized, this is the first register. So for me, this is always the first register. So Anu, maybe you should say whether this is least significant or most significant. There's also a notational confusion there. So do you want to clarify now whether between 0 and 1, what would you say is LSB, MSB?
I think the way when we do the measurement, it flips, the results are represented in the reverse order. That is, the first row goes into the rightmost and the last.
Okay, so
that's how it is represented. The same problem exists even in classical VLSI, the big endian and little endian notations. So it's just a convention. As long as you state here is what we are considering, here's what we are doing, and that's the rule for these questions. I think students can apply that rule.
Okay, thanks, Shesha. So what Shesha just mentioned is that when you measure on Qiskit and then you report the outcome, right, you're actually doing it in this order. Is that right, Shesha? So the
That's
measurement outcomes are described in this order. Is that correct?
That's correct.
Yeah. Whereas when we write them, and so we write them in this order where the first register is sitting here as the first qubit register, the second register comes next, and so on and so forth, right? Okay, so let's quickly analyze this circuit. And so what happens first, there is a Hadamard on the first qubit, and then nothing, which is an identity on the second qubit. Okay, so this is how we would represent this. And what does the Hadamard do on the first qubit? It converts the 0 to a plus, right? So now I have +1. So this is the action of the Hadamard on the first qubit. Now let's expand the state to understand the action of the C0. So this becomes 0 + 1 over √2. And then, like I said, the tensor product is always implied here, okay? 1. And this, because of linearity, you can simply do the tensor product for each qubit separately, right? For each of these registers separately. So this becomes an overall 1 over √2, 0, 1 plus 1, 1, right? Okay, so now this has to get, so this is just the first step, right? This is just the first step after the action of the Hadamard, okay? So let's now do the second step. So the first step was until here. So the second step is the action of the C0. and the C naught now acts on this state, right? So it's 1 over root 2, 0, 1. Oops. So I'm writing this in multiple ways so that people see that it's all the same notation. Okay, I'm now put the 0, 1 in the ket, right? I think in Rama's lectures, probably this is how they are. It's all the same notation, right? When I put the when I put a 2-bit string here, it simply means first qubit is in register in 0 and the second qubit is in 1, right? First qubit is in 1, second qubit is in 1. So the action of the C naught, you know, when the control, so this is the control and this is the target. When the control is 0, it does nothing to the target. When the control is 1, it flips the target. So this then becomes 0, 1 plus 1, 0, right? And this indeed is one of the 4 Bell states. The point is that such a state cannot be expressed. So the output of this circuit, you know, can only be represented jointly, right? It's a joint state of these 2 qubits, right? It can only be represented together, right? You cannot represent the output of the circuit as some state phi here, let's say phi 1 here, and some state phi 2 here. You cannot separate it out into a state of the first register, tensor a state of the second register. So this cannot happen. Okay, this is why this is a Bell state. Okay, so I think the question was about the now in the question, in the assignment, the question says something about, now you take this Bell state and you perform some measurement on it, right? So when you perform a measurement on it, what is the set of possible outcomes that you can get, right? So the hallmark of a Bell state, which is of course one of the maximally entangled states, is that these measurement outcomes are correlated. So let me now talk about measuring a Bell state. So the input to my circuit is now one of the Bell states. Let's say it is this state, for example. Okay. 0, 1 plus 1, 0. Okay. And now this is simply a measurement circuit. Okay. It's just some other circuit which has prepared it. And then I get this state and then now I'm measuring it. This measurement I'm going to do in the 0, 1 basis itself. Okay. Recall that I can measure in different possible bases, right? I can measure in 0, 1, I can measure in plus, minus, etc. I'm going to measure in the 0, 1 basis itself, right? And the question is, are all outcomes allowed? What are the typical set of outcomes that are allowed? So let me call this outcome as S1 and S2, right? So typically, so normally, or let me say in general, right? You can have, you can put a table for S1, S2, and you can say these are the possible classical outcomes, right? These are the 2 classical bits, and I could have this set of 4 outcomes in general, right? This is the set of possible outcomes. But because my input is a particular kind of state, which is a correlated state, actually in this case, it's an anti-correlated state. What happens is if S1 is 0, if the outcome realized here is 0, then the second outcome cannot be 0, right? Because the 2 states in the superposition are either 0, 1 or 1, 0. You do not have a 0, 0 or a 1, 1, right? So if this is 0, then S2 has to be 1. So what this means is this is an allowed outcome set, which is 0, 1. And on the other hand, if S1 was 1, then S2 has to be 0, right? So the other allowed outcome set is this. Okay, so when I write down these outcome sets as 0, 1 or 1, 0, again, this refers to the first register. This refers to the first register and this refers to the second register. So I guess the confusion was also because when you measure on Qiskit, the order here gets reversed, right? But in the question, what I had in mind was in this ordering. Okay, so I hope that clarifies this question. Anu, is that okay?
Yeah, I think yeah, that's a detailed
answer, Prabha. Thank you for answering that. And yeah, so that's the difference in notation that people might have been getting confused, right? But okay, so we'll move on to the other questions. So let me just share screen and
shall I stop sharing?
Yeah, sure. Yeah, thanks. So I'll share screen. I just wanted to show the assignment 2. So in week 2 assignment, there is a link here to the Jupyter Notebook. Some of you have been asking, and the mentors have already clarified. I think a lot of people have been able to code it and have. So I think this should be evident. So once you click here, it will download a Jupyter Notebook, which should look something like this. So you should get a Jupyter Notebook like this, where you have a couple of scripts or parts of it written, and the remaining you have to solve. So there are clear instructions on what exactly you need to write and how you'll be able to find answers to your questions. So suppose for the first question, I've already mentioned what is the state, what you have to try to create, and I'll now show you guys quickly on a demo circuit and how can you create a little circuit and how can you actually access the state vectors. So I've just created a little circuit in here. So as soon as you and couple of people had this question. Sorry. Okay, so a couple of people had this question that whenever you are hitting a plus new cell, the cell is not appearing, and I think that problem has been sorted, or these lines have not appeared, and so couple of lines will already be there. There are some other lines that I have specially imported for the sake of plotting a couple of things. So you can actually do a quantum Qiskit visualization import star, and that's also okay. In my code, some of you observed that I have specifically taken block sphere and histogram and so on. But if you have imported everything, you can ignore that. Again, in another case, people were pointing to the problem that execute was not there. So all you need to do is go to from Qiskit, import execute, and you'll get that as well. Now I'm just creating a little circuit in here, which is for a single qubit. So I have a single qubit and I'm applying an X gate here. So I just drew the circuit in order to show you guys. And this is how you run it on a state vector simulator. So some of you have been asking what are the differences that a state vector simulator and a Qasem simulator has. So this quantum assembly level language, or this Qasem simulator, actually has a lot of it's a very generic simulator. It has a lot of simulating methods that are available, and the state vector method is also a simulation method that is available, and then there are a couple of other like matrix product and other simulation methods that are available in Qasem simulator. So you can very well try that. And one of the reasons why I'm using state vector simulator here is because I want to show you just the output state. So this is the way you get the state vector results, and that's what you need to do for the assignment as well. And you can save the state vector results. You can do a lot of other things here. You can plot it in a block sphere, Q sphere, and whatever you want to. And the other thing that I wanted to mention here, that a couple of people had questions around basis, right? So there could be different bases that you can create, and as Prabha pointed, right? So all you need to form a basis, all you need is two orthogonal vectors. So Prabha mentioned about computational basis, and even in the lectures we have mentioned computational basis, which is the Z basis. It's also called the Z basis, because this basis is formed by the states ket0 and ket1. Which are orthogonal states. Now you can actually form basis by the x-axis, or by the ket plus and ket minus, or the eigenstates of the x gate, and that's called the Hadamard basis, and that's not supported by Qiskit. So in Qiskit, you can do measurements by default. The measurement is using computational basis or Z basis. So what we'll do here is we'll create an X basis. So we're saying that, okay, I've created a little function in here, and this is not a part of the assignment. You don't have to do it for the assignment. But since a lot of people had these kind of questions, so I'm just trying to demonstrate to you how you can actually do it in a number of other bases. And as you understand, in the sphere, you could have several other bases. So you can create infinite number of bases with two orthogonal vectors. So I create a Hadamard basis here by applying a Hadamard gate to our qubit, and then say that, okay, I'm going to measure this qubit in X basis or in the Hadamard basis. I also prepare an initial state, which is and I say that you initialize my quantum circuit with this particular initial state, and it could be in any initial state. So all you need to do is you want to now measure it. You want to measure this particular circuit, and you want to store the results of this this qubit 0 into a classical bit 0. So I've just shown you how you can draw this circuit and actually visualize that, okay, yes, this is the initial state that I wanted to create, and that's what I'm trying to measure. Now again, the same things you can just run it on a backend, and I've again chosen state vector simulator because that's the one that you need to do in your assignment. Again, if you go to your assignment Jupyter Notebook, you see this part of the code is already written there, so you don't need to write it. The main aim of this assignment is to familiarize all of you in how to run it, what are the different mechanisms, what are the different methods available, and so on. It is not I mean, you're not expected to even for the final examinations, you're not expected to know the codes or know like how to run it. You're expected to understand the concept, and that's what I'm trying to explain here. So then you take the output state, you get the result, get state vector, and in this output state you'll actually see the state vector. So then you have to go back and match which is the right state vector in your typical MCQ assignment. And there are a couple of other things that also I tried to do here, and just to show you guys, I'll also share this particular Jupyter notebook and the other Jupyter notebooks in a link, and just keep an eye out on the FAQ channel. So here, if you see, we initialize this qubit to minus state, but even after measurement, it collapsed to a plus state, so or a ket one. And then you can actually do, you can count. So how do you get the counts, and how do you plot histogram, and several other visualizations. So why I'm stressing a bit on visualization, and even in the assignment, I have particular questions around visualization. What is the right visualization to choose, or for what kind of output? How can you see the real component, and how can you see the imaginary component? I just want you to be familiar with the different visualization tools that exist in here. Okay, so that was about question 4 and question 5. Now there was a question which had a typo in here. That was actually question 6 in your MCQ assignment, and it refers to phase flip. We are not talking about phase kickback here. Phase kickback will be introduced in the next week, in week 3, and phase flip is sort of an important concept for introducing phase kickback, and even in it would be very important concept for quantum algorithms. So what we are trying to do here is, I've mentioned that how you have to create this circuit, what are the different things that you have to do. The circuit is already there. All you need to do is write the next lines to execute this circuit, which is there in the demo that I showed you today, or in the other scripts, and you can actually see, or in the video lectures where I've actually executed multiple circuits on different backends. So you can try to execute the circuit and then capture the results, and then you can see what is the state vector, what are the different representations, what are the probabilities, and what are the different visualizations, and how to use these visualizations. So that's about question number 6, and these were the only 2 programming assignments in week 2. Okay, so now we move on to the other questions which are around the theory. And one of the questions that we had from the theory of week 2, which is week 2 lecture 3 at 13 minutes. So a student has mentioned this, that at 1335 instructor states that we can copy 2 states orthogonal to each other. Let's say I want to copy a state. So there must always exist some state that is orthogonal to my state. Shouldn't then cloning be possible? So Rama, maybe would you want to clarify about it without going into too much detail about the proof of no cloning theorem, but just clarify how we can copy states and for superposition, what happens.
The no cloning theorem states something simple. So if you take if you consider what we do in classical computing, one of the most basic operations we can do is copy one state unit, state from one location to another. Like copy a register value from one register to another. You can copy value stored in a memory unit from one location to another. As it turns out, in quantum computing, your qubit is not the equivalent of your classical bit that you can store and record an arbitrary number of times. What the no cloning theorem states is simply that if someone gives you an arbitrary qubit, something value you cannot predict in advance. By value, I mean its superposition state. That is the different probability amplitudes, alpha and beta. Okay, just a single qubit for now. If somebody gives you an arbitrary qubit, you cannot make two copies of that qubit. That is, you cannot pass that qubit through any given quantum circuit and have two copies of alpha 0 plus beta 1. Okay, what you end up with is you can move the alpha 0 plus beta 1 from one location to the other, and in effect, the teleportation protocol that you saw, that is actually doing that. We are communicating an arbitrary qubit from Alice to Bob, but at the end of the process, Alice does not retain the qubit, only Bob does. So what the no cloning theorem says is you can't clone an arbitrary qubit. Now, in the lectures, some of the examples that you saw, what that showed were the fact that for certain special kinds of qubits, you can make a copy. If your qubits are so the mathematical proof that you saw, if your qubits happen to be orthogonal to each other, then you can actually make a copy using a given circuit. So the expression involved using an arbitrary transformation function u, right? So what the proof told us was that if you have if your circuit can be actually, if you assume that the circuit makes a copy and then you take two arbitrary inputs psi and phi, then unless the psi and phi are either equal or orthogonal to each other, you're not going to end up making two copies of phi. You're going to so that's really the limitation. Only if you have two qubits that are orthogonal to each other, you produce a copy. For any arbitrary qubit, if alpha and beta can be anything, then this, you cannot build a general circuit that will make a copy. So that's what the no cloning theorem is saying. So if you have for example, 0 and 1 basis vectors, then if you know, for example, that your inputs are going to be either 0 or 1, you can make a copy. But if you don't know what the alpha and beta are, you cannot. Okay. So rather long-winded explanation, but I hope that clarifies what the no cloning theorem exactly is, how quantum computing is different from classical computing in this very fundamental way. And yeah, you can check out the proofs as well. And if you have access to the book by Nielsen and Chang, then you can make there's an explanation given there as well for why the no cloning theorem is true. Prabha, you want to add something?
Yeah, so thanks, Rama. I just wanted to add one phrase to this, which might help people understand this idea a little bit better. You cannot have a universal quantum copying machine. You cannot have a single Xerox machine, which is going to make copies of every quantum state under the sun. Of course, if I tell you that I'm only going to make ket 0 and ket 1, or I'm only going to make a particular pair of states, I could try and design a cloning machine. So there are things called quantum cloning machines, right? Which can be designed for specific pairs of states. But even then, perfect copies are only possible if those pairs of states or those sets of states are orthogonal. For example, if I tell you that I'm only going to prepare 0 and plus, can you design a quantum copying machine for me? What Anu or Rama can do is to do some optimization and come up with the best possible unitary transformation, which can bring you something very close to 0 and very close to plus. You still cannot make perfect copies of 0 and plus. But if I give you 0 and 1, of course you can always. Why? Because you can always measure. You can measure whether it's 0 or 1, and you then reproduce whatever the outcome is, and there you go, right? You're done. So the point is, you cannot make a universal copying machine which works for any quantum state. If you know that there's a specific set of states, you can try to design optimal cloning machines for that particular set of states. But even those are not perfect unless and until the states are orthogonal. I hope that was a useful addition. So I just wanted to add that point.
That's good.
Yeah. So Rama, there are a couple of questions around teleportation, and even in YouTube live chats, I think people have been asking you. And I know and on Discord you have been answering them. I've also put in the link to Qiskit textbook where you can see the entire explanation, how to run it on a simulator, how to run it on an actual machines. So everything is there on the FAQ channel. But Rama, do you want to explain quickly or clarify the points that have been raised here?
Yeah, I'm not sure exactly precisely what confusion people have about teleportation. I think there was one question on Discord where someone was, I think, confused about the whole idea. I tried to provide an explanation in plain English, explaining what is happening, what is the input, what is getting communicated, and what's output. So just like I mentioned a short while ago, you cannot make a copy of an arbitrary qubit. Okay. But in teleportation, what we are trying to do is, given that two people, Alice and Bob, each hold one part of a two-qubit entangled state, and then they move far away. Okay, the distance doesn't matter. That's it's for dramatic effect. But Alice and Bob move away with one part of a two-qubit entangled state, and then Alice comes into possession of a separate qubit. Bob does not know of the qubit. It's any arbitrary qubit, can have any arbitrary probability, amplitude, alpha and beta. Either way, Alice can communicate this to Bob without, by virtue of the fact that he and Bob share an entangled pair. And it turns out you can. And that's what the whole presentation was trying to take you through. And if you follow the math there, you understand what's going on. What's happening is that you take if you pass Alice's two qubits, that is her part of the entangled qubit, and this arbitrary qubit that only she possesses through the circuit. And then finally she measures, now she has two qubits, right? Finally she measures both of those qubits, and she gets two classical values, classical bits, M and N. What she has to do is she has to send those classical bits, M and N, to Bob. Bob, given his pair, his part of the two-qubit entangled state, will pass that entangled state through some combination of X and Z gates, and the number of X and Z gates to be applied is determined by what value of M and N he gets from Alice. How does he get these values from Alice? We assume that there's some classical computing channel, like I mentioned, somewhat jokingly on the chat. Alice can pick up a phone and call Bob and tell him M is 0 or M is 1, or N is 0 or N is 1. So once Bob knows that, he passes his previously entangled qubit through the circuit, and it turns out what he gets recovers from that is identical to the arbitrary qubit that Alice came into possession. Okay, it may sound like magic, but if you follow the math that in the presentation, you'll see that this is exactly what he gets. Okay? And this is a very unique property of quantum computing. It's something that quantum circuits can uniquely do, which classical circuits cannot do, and it provides us a very powerful tool for building quantum algorithms. Is that sufficient, Anupama?
Yeah, so there were these two questions around,
Yeah.
how does, so Yeah, I'll just tell you the question. So how Bob will know that he has to get back the same state phi? So as you clarify, like Bob doesn't know what is the state phi that he's going to get back, but after Alice has communicated and after on a classical channel, then Bob can get to know the state.
Yes.
So yeah, one question here for Prabha, and I'll just read out the question, Prabha. So why is that in quantum mechanics, every time a vector is expanded in a linear combination of eigenstates of some observable, the coefficients always represent the probability amplitude?
Yeah, thanks. I saw this question too, actually. Yeah, so the answer is quite simple. When I expand in an orthonormal basis, an orthonormal basis is something which can always, for which I can always construct a measurement. I can always associate a measurement with an orthonormal basis, right? Because we've seen this in the measurement postulate also. It's something, measurement is a kind of operation or a transformation which collapses the state that is being measured into one of a set of orthogonal states, right? So every time I expand a state into this set of orthogonal states, at the back of my mind it's as if I am measuring this state, and the corresponding coefficients of expansion of that orthonormal basis then give me the probabilities of the corresponding outcomes in a measurement. So the association is that if I have an orthonormal basis, it can always be associated with a physical measurement. And so those superposition coefficients get a physical meaning in the sense that they are the ones which tell you the measurement statistics for that state when you measure in that particular orthonormal basis. Okay, and the fact that the state is normalized goes back to the fact that this is a valid probability distribution, that the sum of the mod squared of these coefficients sums to 1, right? It's just probability conservation is what leads to normalization. So this is the sort of connection. I hope that would clarify the question.
Yeah. Okay. And yes, so there was a question around, can you please clarify what it means by measuring in computational basis, superpositional basis? So I've created a little script, the script that I showed you guys, and I'm going to share that and explain in detail that, and as Prabha mentioned in the Bell circuit one, right? So how can you measure it in a computational basis? I've also created snippets in how can you measure in the X basis or in the Y basis, and what kind of results you get for you to visualize that. So the X basis one I showed, and the Y basis and others I'll share the script so that you guys can see that. Yeah.
Sorry to interrupt. Just there was one, I think there's one question which I see even today in the YouTube live and also probably in one of the forums about what does it mean to say that I have a Bell state in the 0-1 basis? I'm writing my Bell state typically in the 0-1 basis, right? What does it mean to visualize the outcome in a different basis, right? And I think there's also a question in the assignment about this. You think it will help if I briefly show just a couple of steps of math, which will kind of help people understand what one means by visualizing the state in a different basis, right? Okay, so I'm back to the same notebook which I had shared earlier, where I had shown you how to read off essentially the outcomes, right? So if I have a state of this form, so if I have a state in the Bell basis itself, so measuring, let me say in a different basis, okay? I think that's the sort of common confusion. So let's say I start with the so-called first Bell state, right, which is 0, 0 plus 1, 1. Now, if I measure this in the so-called computational basis itself, which is the 0, 1 basis, right, then it's very easy to read off the possible set of outcomes. And remember, reading off is exactly like this, right? I measure, I'm doing a measurement. Actually, maybe I should draw two separate boxes here. I'm doing a measurement on the first qubit, and I'm doing a measurement on the second qubit, right? And I'm measuring the 0, 1 basis here. I'm measuring the 0, 1 basis here. So that's what this means. So you can visualize this as a circuit where there are these two measuring devices, right? acting on each qubit. This is what your the script that Anu has written. For example, if you visualize on Qiskit, this is what it will look like, right? And each of this is a measurement in the 0-1 basis. It's easy to read off the outcomes because you simply look at what are the states in the superposition, right? There's only 0, 0 and 1, 1, which means if the first outcome was 0, the second outcome has to be 0. If the first outcome was 1, the second outcome has to be 1. So if I write down what are the allowed set of outcomes, then this is, like I said, always 1 and 2 for me. This is qubit 1, qubit 2. So the allowed set of outcomes would be 0, 0 and 1, 1, right? Okay, now if I were to ask what happens if I measure instead of the 0-1 basis in the plus-minus basis, how would I visualize this? So the first thing to do is, if I want to understand what the measurement statistics look like in the plus-minus basis, I think you can call this the Hadamard basis or the, Anu, this is what you're calling the superposition basis, right? Isn't that right? Just want to confirm.
Yes, the superposition basis or the Hadamard basis.
Hadamard basis, indeed. So the first thing to do is to transform this state itself into the plus-minus basis. Okay, and once you do that by hand, then you can again read off the outcomes exactly like how we did for the 0-1, right? So how would I do this transformation? Well, you know the relations, right? So you know that 0 is plus minus by root 2, and you know that 1 is plus minus over root 2. So then what does this Bell state look like in the 0-1 basis? I'm just going to show this to you very quickly. So you simply have to replace your 0, 0 in terms of plus and minus, right? So there's plus, minus. So there's going to be an overall half here. And there's going to be plus, minus and plus, minus. Okay? Plus, minus. Again, a half here. Plus, minus. Okay? So I'm simply using these two relations and substituting them here. Okay. And there I've got the state in the plus-minus basis. I simply now have to do a bit of algebra to see which are the terms that actually survive. So you will see that this minus plus term out here and this minus plus term out here comes with a minus sign. Similarly, you notice that there's one more minus sign out here, which this plus minus term and this plus minus term, right? They come with a minus sign. Okay, so I hope you see that this actually evaluates to plus, minus, right? Because I'll have plus, and half, so that's 1. The minus plus here sits with a minus sign. This, the minus and minus together give you a plus for the minus. So I can also write this as plus, minus, just to say that this is all the same notation. So now, of course, you can, so please check this, okay? And this is the most interesting or one of the, many fascinating features of the Bell states. And that was probably the reason this question is there in the assignment as well, is to show you that it doesn't matter whether I'm in the 0-1 basis or in the plus-minus basis, at least with this Bell state. Of course, you have to go check what happens with the Bell state, which is given to you in the assignment. But at least with this Bell state, you notice that the correlations are exactly preserved, right? So it doesn't seem to matter. And this is a very important feature which is exploited for secure quantum communication and things like that. So the correlations are actually preserved across the bases, right? So now if I measure this state in the plus-minus basis, then you notice that again, the possible outcomes, right, can only be plus and minus. They're perfectly correlated outcomes. If the first qubit gave you a plus, the second has to give you a minus. The first qubit gave you a minus, second has to give you a minus, and so on and so forth. You cannot have the outcomes plus minus and minus plus. Okay, so the correlations are exactly preserved. So this is what one has in mind. This is a kind of probably approach for you to think about that question, right? Where you say, take the Bell state in a particular basis and try and look at what the outcomes will look like in a different basis. Okay, so I hope that helps.
Yeah. Okay, I think that was I think that was the next question, that after creating Bell circuit in experiment 4, we measured both qubits Q0 and Q1 simultaneously. We get the desired Bell state. Why do we need to measure in various bases like computational superposition and joint computational basis? Yeah. Okay, there is one more question, one last question, and I know that it can be answered in 2 different ways. So this question, maybe Prabha, you and Shesha, both of you can answer in 2 different lights. So there's a question on how gate operations actually work. I have put in a link to Quantum Global Summer School, wherein they explain how it actually works in IBM quantum computers. But maybe Prabha and Shesha, both of you can cover it in terms of how gate operations work in IBM quantum computers or the physics part.
So Shesha, if you want to go ahead, that's fine. And if this is about how they are physically implemented, right?
How
so
they're physically
the question was, we see the math, what does it mean physically? The physical realization of a gate, what does it really mean? Maybe you can, since you're more used to spin way of doing it, maybe you can explain what that is mean in a spin realization. I'll just give an overview of how it is done in IBM hardware. So in IBM hardware is transmon qubit. It's what is called as an artificial atom. And what we do is we look at it, the lowest 2 energy eigenstates of that particular artificial atom. If you see a picture of the superconducting qubit, and I know if you have some picture of superconducting qubit, just show them that, the chip. You have these wiggly lines going into that qubit from outside, and there are wiggly lines connecting 2 qubits. So those wiggly lines are called waveguides. Basically, you shine light at certain frequency in that, much like how lasers work, much like how a lot of communication happens through light. It's the same thing. It's just that the frequency of operation is a microwave. Microwave is a very low frequency operation in the energy spectrum. And then you have on the higher end is the gamma rays and other things of very high energy spectrum. This is on the lower energy spectrum. Typically, what that means is you send a set of wave packets into the waveguide. What that is a bunch of wave functions that you send. It's essentially frequency of the light that you shine into it. It goes into it, hits the qubit. Based on the frequency that you are sending, there are two modes. A signal that can have is what is the frequency that you're sending it in, what is the amplitude, and what is the phase. That is, how long are you sending that signal? All 3 matters, but for simplicity, we'll ignore the amplitude. But it's the frequency and how long you send that signal. What is the shape of the signal that you're sending? Is it half like this or the full sinusoidal? It means different things. So for certain gates, for example, you can send, say, pi over 2, just a signal that goes like half of the sine wave, perhaps. That's the signal that goes in, hits the qubit. And what it does is, if you work out the math, basically it rotates the qubit. Say if it was in 0, it can probably flip to 1 or 1 to 0 based on the state that you are in and based on the signal that you're sending. So physically what it means is you send a microwave signal through a waveguide, it hits the qubit, and that qubit reacts based on the frequency that it's being sent and the duration, the kind of signal envelope that you're sending. It reacts to it based on that, and based on that, it's going to rotate. The rotation can be this, or it can be in a superposition state. A different frequency, if you send it, this is called the detuned frequency. That is essentially the difference between the if you send it little more than the difference between the top 2 things, it's a detuned frequency. If you do that, what it does is different qubits, neighboring qubits have different resonance in a way. So if you send a different frequency in the same signal, what it does, it has a coupling between the other qubit, and that's how 2-qubit operation happens. And the math, the way you work it out, it can be a control Z or control phase based on the basis that you're using, based on the physical realization of it. So physically what it means is essentially sending a signal of light through a waveguide and hit the qubit, and based on the frequency and the shape of the signal, you will perform the gate operations. So typically in IBM hardware, it's a microwave frequency. The signals are typically anywhere between 4 to 8 gigahertz is the frequency that you send it in. When you do that, typically the 4-6 gigahertz is for single qubit operation, a little bit higher. is for 2-qubit operations. There are different ranges that you do, and when you do that, you get different qubit. And again, it's the number of neighbors. You do different frequency for different neighbors, and that's how you make a 2-qubit gate between two different neighbors.
So I think that was pretty comprehensive, Shesha, and I don't have actually much to add about the spin qubits, except to say that the idea is exactly similar, except that what you use now are RF pulses typically in the spin case, is my understanding. So it's the same thing, and you can visualize, in fact, the spin operations on the Bloch sphere. So you know that the north pole is your 0 state, the south pole is the 1 state. So this basically gets triggered, this flip can get triggered via some RF pulse, right? Similarly, rotating along the XY plane is also a different kind of pulse, right? So there are different pulses, whether it's nuclear spins or the silicon qubit, the electron-based electron spin-based silicon qubits. It's all different electromagnetic pulses of different wavelengths and frequencies, right? And typically in the spin case, like the NMR and so on, these are RF pulses that are sent, and they have different names like a pi/2 pulse and a pi pulse, and they will realize your different set of single qubit gates. Right. So I think the idea is exactly similar, like what Shesha explained with the superconducting qubits.
Okay. So that was more, I mean, all the questions that were the most frequently asked questions for this week and last week's assignment, and in the course channels. So and thanks a lot to the TAs who have been monitoring YouTube Live and answering the questions that have been coming in around in YouTube Live. So yeah.
Yeah, sorry, I just wanted to clarify one point which I see coming up in the YouTube chat repeatedly, this idea of what is an entangled state versus what is not, right? And we have seen one kind of example where in the same basis, which is the 0-1 basis, we have these two qubits being correlated, right? Something like 0-0 plus 1-1, where if one qubit is 0, the other qubit has to be 0. If one qubit is 1, the other outcome has to be 1. I just showed you with an example of how you can rotate this to a different basis. You can rotate both qubits to a different basis, which is a plus-minus basis. And again, now you can talk about entanglement in the plus-minus basis. But what if your two qubits were in different bases? Okay, can you still talk about entanglement? The answer is indeed yes, right? Because every basis is like associating with it with a different observable or a different measurement, right? Two measurement outcomes being correlated is what entanglement is all about. It does not matter whether the two measurements are made in the same basis or in different bases. I could, for example, have a state where the first qubit is measured in the plus-minus basis, the Hadamard basis. The second qubit is measured in the 0-1 basis. Okay, but still these outcomes are correlated in the following way, that if I get a plus in the Hadamard measurement, I always get a 0 in this measurement. And if I get a minus in the Hadamard measurement, I always get a 1 in this measurement. So that's a correlation, right? So when one asks whether a state is entangled or not, the idea is to, you may have to do a bit of algebra sometimes. You may have to stare deep into a state to see how things can get combined together, whether it factorizes into two independent states on the two qubits, in which case it's not entangled, there is no correlation between the outcomes, or whether it gets mapped to this kind of a superposition state where the two outcomes are correlated, maybe in the same basis, maybe in different bases. Okay, yeah, I just wanted to mention this point.
Okay. Thanks, Prabha. Thanks, Rama. Thanks, Shesha. Thank you all. There are a couple of other questions, and I'll be answering them on YouTube Live as well as on Discord and Google Forums. But yeah, thank you all for joining.
Thank you, Anu. Thank you all.
Thank you.
Thank
Thanks.
you. Bye.
Thank you. Bye.